Yeah, I think even if I haven't finished by 12:30, you're meant to get up and go. Yes. Yeah. Okay. Yeah, great. Just a couple of things when I was unable to answer the questions yesterday. A vacuole, someone was asking me about that, is just a membrane enclosing a water-filled space, which then the cell puts in proteins or uses it to divide up two bits of cell. So it's basically a biological bag made of a shell, which is just a biological membrane. I think this energy at zero Reynolds number thing you'd sorted out for yourself by the time we got to the end of it. But yes, remember at zero Reynolds number, you put on a force and a velocity distribution is created instantaneously. There's no sort of propagation of momentum. That velocity distribution will have gradients, and it's those gradients which give rise to viscous dissipation, which balances the energy you bung in from the force. And if you look at Stokes' equation and multiply it by V, you can see that balances very easily. If there are any more, I'm sorry I've forgotten, come and ask me afterwards. So this is what we did yesterday. We now have to look at the active stress, because what we're trying to do is say, okay, this is active turbulence. The things swimming around, those little micro swimmers, are setting up flows in the fluid, and so they're setting up additional forces, additional stresses, and we've got to understand how to put those in the equations. I argued that because of the symmetry of the flow field, it seems reasonable that you want to start with the pneumatic equations of motion. And so I wrote down the equations of a pneumatic liquid crystal, and those are well understood, although we didn't derive them, that would be very hard, but they're well understood, people understand them. And I'm now going to give you the answer, and then I'm going to reproduce the argument that leads to the answer in a fairly waffly way. That's best we can do, and best is very good, a fairly waffly way, okay? So the answer is that all you have to do to make this pneumatic an active pneumatic is add a term like this. It's a term which appears in the stress tensor. You add it to the stress tensor. It appears under a derivative, and that's important. And it's really simple. It's this theta thing, which is just the magnitude of the activity, how strong these little swimmers are, the magnitude of the flow field they're producing, times Q. And that's all it is. Of course, it's in the continuum approximation, and so it's a leading order term that gives you this activity. Because it comes under a derivative, any gradients in Q are going to give you forces and going to give you flows. This is going to be a non-zero bit if you have gradients in Q. And that's a really important story, because just by saying gradients in the order parameter, either in its magnitude or in its direction, gives me forces, gives me stresses, then things are going to happen. So I can explain almost anything that I want to using that. So let's stop with the slides for a minute and, oh, sorry, yes. That's what I'm going to do now, the best we can do. All right, up to now, it just is plausible because of the symmetry. And it certainly is not a proof in any way. It's just a plausible thing. Yeah?
How is that term different from the gradient term about free energy? That's also derivative.
No, it's in a different place, basically. Right, this is a stress term. That one is equilibrium statistical physics. That would be just in the equilibrium with no flows. This one's in the equations of motion. Yeah. Yeah.
I know the last time we discussed subtle coupling the S term, but we wanted to if you go to here, these broad brush
I'll say it again, okay, but I'm not going into detail with it, which is basically I've got molecules or colloids like that. If I have a shear, it means that the flow there and there are different, and so it's going to turn the thing. Okay, and that's that term. That's the physics behind that term. Yeah. Yeah. It's just terminology. These things are different. Okay, they're different because they don't come to thermodynamic equilibrium. There's no detailed balance. And so that's become called active. And I think it took a while for people to, I mean, people were calling them active. It took a while for people to actually define what active means. And it's stuff which is continually transducing energy on a single particle level. That moves you from extensile to contractile. It just changes the sign of those little dipoles. Yeah. Yes, this is essentially a leading order term, just like it always is in Navier-Stokes. Right. Kind of get on with it because that was the easy bit. Okay, so I mean, this is the physics and this is the important punchline. And if you don't understand what I'm doing now, it really doesn't matter for the rest. All right, but I'll try and do this. It's a fairly, it's an argument which was given by Simha and Ramaswamy quite a long time ago now, maybe 10 plus years ago. It's a really nice argument which leads to this, but there's quite a lot of hand waving that goes on. Okay, so I'll go through it, and there are places where it isn't, you know, it's Shriram Ramaswamy doing physics very cleverly to get the right answer, like that. Okay. Right, so it really is starting from the microscopic and then trying to get to this. So let's have a little swimmer. X alpha is the position of that swimmer, and alpha is my swimmer label. So alpha. We know that what's special about these swimmers is that they need to exert equal and opposite forces on the fluid. So the very simplest swimmer model we could have is one which has a force here, which is equal to a force there, which acts at the ends of the swimmer, but I've written them down here so that I can see what I'm doing. N is a unit vector along the swimmer. It has an alpha label because it belongs to that swimmer. And a force in this direction, N alpha. Let's say it has strength F. And so this one has to have the same strength in direction minus N alpha. Got it all? I need a length. I need a length of this thing. Let's say that it's of length 2a. All right. And then this point at this end of the swim is just a point x. And the coordinate of that point at that end of the swimmer is x alpha minus a n alpha. Well, no, it's a sort of length scale, right? This is a very, very simple swimmer model. This is an individual particle, so it's sort of an order. But of course, things are just long lines. But if I was looking for a long way away at this swimmer, so I was just taking the leading order multipole, that's what it would look like. So now I want to write down the resultant force due to those two ends. I'll write down the ith component of that force. Okay, and this is the active force. What's it going to be? Well, it's just adding up those two forces. If I add them up, what I end up with is F n alpha I. And then I have a delta function because one acts at one end and one acts at the other end. Okay, so that's one end. The other one is at x minus x alpha plus a n alpha. And I want to find the total force per unit volume, say, and so I add up over all the swimmers in my unit volume. So now I want to just do a Taylor expansion on that, because I want to basically look at the difference between these two terms to leading order. And so I'm going to write down a Taylor expansion of those delta functions. And the way to do that, you have to remember when you sort of did Maths 101 and they told you how to do vector Taylor expansions. This is going to be approximately equal to, I've got sum over alpha, I've got n alpha I. Doing the Taylor expansion on that, the leading order term, if I forget about the small bit, will cancel out. And I'm going to end up with the difference times the derivative of function. So I'm going to end up with the gradient of delta x minus x alpha, okay, times n alpha j. This is the vector version of a Taylor expansion, right? It's equal to the function plus the derivative of the function times the small bit. J is the repeated index because I've got an x, y, and z component. Then I have a minus 2a, I think, from this small bit here. So I've got a minus a n alpha times that, minus another a n alpha times that. Can I remember the bits? Yes. Okay, so now I have to worry about what I want to do with that derivative of the delta function. If I integrate by parts, what I can do is I can take that derivative of the delta function and I integrate that bit and I differentiate that bit. And so I can put my derivative here. Okay, so it's now acting on that bit of the term. And I need to change the sign, but I actually don't need to change the sign because I got it wrong the first time, because I'm expanding around the center of this swimmer x alpha. So I've got a minus sign from there as well. Okay, so that's easy if you can remember what the Taylor expansion does. It may be, but I refuse to find factors of 2 in the middle of lectures because I get myself in a complete mess. All right. Okay, but I am going to put in a factor here, minus 1/3, and I'm fine doing that, right? Because it's under a derivative, so it isn't going to make any difference. And the reason I'm doing that is because then that looks like Q, which is a Q tensor. So let me take that thing now, and have I got it how I want it? Yes. And now this is the fiddly bit. I'm going to coarse grain that. At the moment, it's right, apart from the approximations of the Taylor expansion. But what I want to do is average over a region. And there's no real proper way of doing that. You have to just do something sensible. And the sensible thing is to take this term here and say, right, that term there is just Q, my Q tensor. Remember, the Q tensor was equal to something proportional to Ni Nj minus 1/3. So what I'm really doing is replacing the N alpha of my little swimmers by the local order parameter, the local director field, N alpha. Here, I'm taking an average, if you like, over swimmer. Then I've got a sum over alpha of delta x minus x alpha. So I'm adding up over all my little swimmers. That's going to give me a concentration. C is concentration. I have a -2a, all right, and I think, well, I've got an F, which I've missed out. Way down. So that's what I've ended up with. And I've also meant to have a gradient term in here, which is very important because if the swimmers are all moving in the same direction and there's no gradients anywhere, the flow fields are going to cancel each other out. Yep. And what you're going to end up with is no additional stress. That was a force per unit volume. The force per unit volume is related to the stress. So my force, that's the active force. And so I can just read off from this what the active stress is. It's the stuff under the derivative. And so I end up with an active stress, Ij, is equal to minus zeta q Ij. Okay, where this q is the order parameter. That zeta tells me about the strength, the local strength of the activity, and that makes sense. It's equal to the local number of swimmers times their dipole moment, force times the distance between them. All right. And that is a hand, well, I mean, the coarse graining is obviously a bit hand wavy. That's where this comes from. That's the best anyone's done, I think, to derive this. And it'd be interesting, actually, I was trying to go through this just to see if there's a more mathematical way or a slightly more, a slightly better way, well, yeah, more precise way of doing it. But that shows the symmetry and it shows where the Q comes from. Anybody would like to point out a bug in there? Because I've been struggling with a bug, which I think is an well, not a bug, an interesting approximation. Anybody like to tell me what it might be? Or okay, I've assumed my concentration is the same everywhere. If the concentration varies from place to place, that will set up stresses because the flows won't balance perfectly. Okay, and it was not obvious to me as of a couple of hours ago exactly, or whether you can put this in there. I think you probably have to do the coarse graining more carefully to put in that additional term. Yes. It's the same sort of thing. If any of these terms vary from place to place, you will get an extra stress. And this is not in that derivation, and you'd have to start again to look at those differences. Okay. Well, it's when you do the coarse graining. All right. Yeah. I was having a terrible trouble working out because I need a derivative here, right? And where it comes from is this having to switch. Yeah. It's more the next door one has to be bent a little bit, but you're quite right that if I have a load of dipoles which are looking like this, exactly lined up, and I work out their flow fields, they will all cancel and nothing will happen. The minute I do something like that, or put slightly more of them here than here, you won't get the cancellation. Okay, this bit takes account of the changes in Q, but you could have different changes, which could actually always be included in that Q. So this is only a partial derivation of that. Yep.
This is specifically for pneumatic after polar.
In fact, you're okay if it's polar. If you
and the forces have two sides.
It's more, even if it's polar, the swimmers will have to have this sort of balance of forces because they're still autonomous swimmers and they still.
Suppose they're like a little engine that's spinning down.
Yeah, but no, they're in a fluid. All right. So if you want to go to polar, what you have to do is you have to make that A prime and that A, and that will give you the asymmetry. You're not allowed to not have balanced forces because they're autonomous swimmers. Okay, but if you want to kill the pneumatic symmetry, you can do that. You can go through the whole thing again, and you end up with the same answer. So even polar things have this zeta q as their hydrodynamics.
Why can't you consider that moves only propels itself in some direction
Right.
along its axis?
If it's on a surface or something like that, it can do that and it can push itself. But for these swimmers, what makes it move in a certain direction is the this local loop of states it has to go around, which has an area in it. You have to have a stroke which is not time reversal invariant. At any time, the forces have to be equal and opposite. It's what we were going on about yesterday, okay? It's not an official swimmer if it doesn't have these equal and opposite forces, because there's nothing there to push it, right? If you put a cell on the surface, it's
I mean, there are active matter that is polar, that can generate propulsion.
that's right.
Some chemical.
That's right, but it still has this flow field. Yeah. Yeah. Whoops.
So you get parts. I'm sorry, I don't see the, where's the interval?
It's in my head. If I did integrate by parts, right, that's what would come out at the end. So I'm being waffly here, yes. Because else I don't know what to do with the delta function, basically.
The sum over alpha, that's
Sort of, yes, yeah. No, and you'll probably get that for Yehutu, who's going to talk next week, right? Is someone who's really expert on these polar systems and wrote down the continuum equations for polar systems. Is responsible for that, okay? If these polar swimmers are in a background fluid, you'll still have this zeta q, but you will have extra terms in the equations of motion, which says that the whole thing has a net velocity. Yeah. But see you next week, because he'll be able to do it much better than I can. Okay, right, so let's start from here now. What are the consequences? Well, the first consequence is that the pneumatic state is unstable. If I have this nice array of swimmers, all the flow fields will cancel. If I have a small fluctuation, which you always do, right, I have a gradient in the order parameter, and that induces flows, it induces stresses. And if you work it out, they go in this direction if you have an extensile system. So what happens is that that state is unstable because it's going to just bend more and produce more flows. It's going to bend more, okay? The pneumatic state is unstable to activity. If you have a contractile system, you're okay because these arrows reverse and this will fall back to its ordered state. But unfortunately, if you look at a splay deformation, one like that, that is not stable. So you've had it anyway, okay? A pneumatic state is unstable to activity. What I'm doing here is a pictorial version of a linear stability analysis. I don't think so. I think you just put in a wave in your equations and yeah. It really is just a linear, it's an instability, a linear instability.
So we just have like normal stresses in our system, right?
Think of it as the way these swimmers set up stresses in the surrounding fluid. And if you start thinking of two swimmers, you get in a mess because this is a coarse grain picture of lots of swimmers. So what you need is a sort of gradient of swimmers. So we can't, I mean, there's lots that's been done on individual swimmers, but this is a continuum version, a coarse grained version of what's going on. where were we? Okay, so let's have a look at a picture and actually have a look at these instabilities. Now, this is this microtubule motor system. The trouble is with this, if you turn off the activity, if you kill the motors somehow, the whole thing just sort of gets into a nasty, messy soft matter clump. So it's difficult to get them lined up to see the instability. So this is a clever experiment when by the group in Barcelona, where they put a straw into the active matter. So you've got the active matter sitting on the surface, you put in a straw, and some poor graduate student sucks. And then the next one comes along, you sort of poison them gradually, okay? So that means that the microtubules line up towards the straw, and you get a radial load of microtubules which are lined up with each other. And so you've got the starting state you want of everything lined up like a pneumatic, almost. Radial doesn't really matter. And then you can watch it become unstable. So I'm going to play this twice because it happens quickly. So you have to be ready for it. It's lined up. There it is. And there you see those waves forming. Those are the instabilities actually forming on these things. Okay, so you start with the instabilities going up and down like this. And if you look very carefully, you then get secondary instabilities like that. Let me play it again because it sort of all happens all at once. Sorry, I'm going to get back to the beginning properly. Right. So this is lining them up. And there you can see those instabilities starting. Clever experiment, that. Yeah. You go to the equations and it's the square root of K, the elastic constant, divided by the activity. I don't think that's obvious unless you do it from the equations. Yeah. It's this motor protein microtubule system. So this is that system. Yeah. Yeah, it does. Sort of, because if I have these things pushed like that, yeah, it's like having a force upwards here and an equal and opposite force downwards there. So I could replace my swimmer by a sort of very close together pair of microtubules. Yeah, but it's a good question. It's not, you have to think about it. It's not so obvious. Microtubules might be more wriggly, for example. Yeah. Good question. And actually in 3D, they have to do that because they need the passive background pneumatic to make the active ones sufficiently strong. The thing you might get is separation into the active and the passive regions. Don't think you do. Where's Marana? Do we? That's what I'd worry about. I think you don't. I think it doesn't automatically phase separate, but I'd have to look that up. I mean, it's sort of a research question to ask if that happens. If I have cells, for example, with two different sorts of activity, do they phase separate? All right. And the theories sort of tend to say no, and the experiments show that maybe they do. But it's hard to get thermodynamic interactions and active interactions separated there. Sorry, I'm getting off track because I think that's an interesting question. Okay, so we've done that. Right, so we decided that we have an instability. Next question, what do we get instead? And then it's hard to do anything analytic, so we solve the equations numerically, and what you end up with is active turbulence. We've seen this lots of times. This is the experiments. This is actually the velocity field that you see. The velocity field that you see if you do simulations. The yellow bits are larger values of the velocity, and in particular you see quite a lot of vorticity. This is the vorticity field. Can't remember whether it's from experiments or simulations, but it looks statistically identical. Why has it done that? It looks statistically identical. And if you plot things like a vorticity correlation function, they match very well. Red bits are anti-clockwise vorticity, blue bits are clockwise vorticity. That length scale is about 5 to 10 swimmers. What you'd plot is the vorticity correlation function as a function of distance, and you just get this, okay, which says that I've got vortices. The length scale is about 5 to 10 swimmer lengths, okay, and what you're seeing in that sort of shape is these sorts of patterns. Not obviously, no. It's just going down. Nobody, I think, has, there's not very little theory. All right, this is just measurements. And you find it's the same in the simulations of these equations of motion and in the microtubule motor protein experiments and in the swimmer experiments and so on. Yes. Yeah. People have looked at that, but yeah. Okay, so let's just sort of zoom in on these simulations just to see if they're doing what we expect them to do. So this is just taking a microscope and zooming in on the simulations. And what you can see on the next slide is that here you get a very obvious bend. These little lines of the pneumatic director, you get a very obvious bend. The director is changing. Changes in the director cause stresses, cause flows. This is pushing one of these large scale flows, and then basically the whole thing gets in a mess because of a combination of these instabilities, which are giving you the bends, which are giving you the flows. And that is active turbulence. Okay, so this is a liquid crystal. Do we get topological defects? So let's look at the topological defects in these systems. Slight cheat to call them topological defects because you only now have short range pneumatic order, doesn't go on to infinity. But let's look at the things which have the same shape locally in the director field as I expected in these two-dimensional pneumatics. So this, remember, this is the +1/2 comet-like ones. These were the -1/2 ones. The red dots are wherever in my simulations you get a +1/2. The blue dots are where you get a -1/2. And if this was a passive system, what we would expect is that the reds and blues would come together in pairs and annihilate each other because that minimizes energy. So let's see what actually does happen. Hopefully you can see them coming together in pairs and you have to get the right ones. Okay, so that's what's happening. Then look up here. I think it happens there.
They disappear, but what creates it?
Okay, so they disappear, but then they're also created in pairs. Okay, so that's what makes this very different for a passive system. And that's exactly the right question. Why are you allowed to get them created in pairs? And the answer is that this is active. You're pumping in energy. There's energy there. The energy is able to overcome the elastic energy to create these defects. So you have enough energy available to create the defects. Essentially, yes. I mean, you, yeah.
I was just wondering whether characterize the station distribution
Yes. It's something we know what the answer is. I'm not sure we understand it. Okay. Because we can measure all those things and did measure all those things. You know, things like, in fact, this active length scale root K/zeta tells you about the distance between the defects, things like that. You know that if you put in more activity, the defect, you get more defects, things like that. But that's not the same as having a theory, and we don't have a theory. Yeah.
So is there a knob you can turn so that primarily get isolated back to
I mean, that's what everyone always says, costless salus, but this is non-equilibrium. People have had a go at it. Yeah. People have had a go at this and not been able to map it onto a Kosterlitz-Saulus-like system. You can sort of map it onto a gas of defects, but I don't think anyone has actually got it right. People have tried, but
Yeah, I wouldn't
I
map
can-
it on the exact model.
yeah.
I'm just curious though if there's a regime in which the red and blue dots are mostly close to each other. As opposed to
we don't see any sort of phase transition in that, no. Yeah. People have tried to rewrite this as a defect dynamics. So using the dynamics of these defects, viewing them as particles. Okay. E.g. Cristina Marchetti has had a go at that. I mean, it's a valiant effort. I don't think anyone really has got it right yet. Yeah. It's not that easy. Yeah. Well, if you think it's that easy and you can do it, that's brilliant. You'll be famous. Yeah, sorry. No, you need something with a source and sink term. On average, they're conserved, but it fluctuates around a mean. The number for the number of pairs. They're always created and destroyed in pairs. Yeah.
Can you turn down the energy input to get the pairs staying close together, or does that not work out?
If you turn down the energy input, you get less pairs, and eventually you can have an active system which doesn't create defects, because to create defects, you have to get over an energy barrier because you have to locally sort of twist the order parameter. And so eventually you just don't have enough energy building up for that to happen. Yes. All right. They have very weak interactions, but that's a good question, because if I create a pair of defects, right, and they're sitting next to each other, then you would expect them to annihilate, because elastic energy makes them attract each other. So the extra thing about these defects is that they are self-motile. The plusar halves move on their own. They move due to the flow field, the background flow field, but they also move on their own. They're self-propelled. And we can see why with this sort of mantra about changes in the order parameter. It's pretty obvious that there are changes in the order parameter here. Cause stresses, cause forces, okay? So this thing's going to have a force on it. And just by symmetry, it's either going to move towards its head or towards its tail. And actually the extensile ones move towards their head and the contractile ones move towards their tail. This one here will also create flows. Again, the order parameter changes, right? The direction changes, but they're balanced flows just from the symmetry. So it's going to create flow fields, but it's not actually going to move. So what happens is a pair is created and the plusar half zooms away, and then it probably will annihilate with another one. I've got a slide which says that, so I might as well play it again. This is actually the same movie, yeah. If you plot the distribution, there is definitely a distribution. As far as I know, there's no real theories to predict that. There's a nice paper by Luca Yeomans about 5 years ago, which I can show you, which is which does something about that. Yeah, yeah. So we can measure all these things, but not really predict them. Yeah, yeah. Okay, so if I have a passive system, no active stress term, I can have a pneumatic state, which at 0 temperature, everything is perfectly ordered, yeah? And I can have proper topological defects where long way away, I mean, they have an infinite energy because they muck up the director field all the way to infinity. So strictly, you need an infinite, perfectly ordered system to have a proper topological defect. Here we call topological defects because we're so used to it from passive liquid crystals, but that's cheating a bit because in fact you can unknot them, you can change things because you get these local patches of pneumatic order, a bit hard to see here, but locally those are all going in the same direction and those are all going in the same direction, but they don't go on forever. The activity is mucking them up. Activity will always kill range pneumatic order. Long range means goes on forever, short range means doesn't. Yeah.
It's always occurred in pairs, and some places flow one defect appears. How does the flow in another place know that needs a second?
They always appear next to each other
They don't get destroyed immediately.
because the plus or half moves away.
I would thought that the fact that you can't be a single one would be connected to the fact that it's a true topological defect, but not topological defects, or if they don't cost infinite energy.
Yeah, that's a good point. He's saying that the fact that you have to create them in pairs means that they count as topological defects because you have a conservation of topological charge. You always get plus and minuses in pairs. I think that's a matter of what we define as topological. Okay.
But then in what sense does a single defect not have energy?
You mean in a real system? Okay, a single one doesn't have an infinite energy. I mean, I think if you put a little loop around that one, okay, I think because everything's so messy out here anyway, you haven't got the structure of the field. They're created in pairs just because locally you have to have that structure to get two of them appearing. Yeah.
Any other length scale cut off the block you might be
Yes.
The simulation, it looks like the directions that the labs
Essentially, it's an artifact of, I mean, we have to be careful because that can happen. But essentially, it's lousy graphics because what we wanted to show here was the defects and not the background director field. Yeah. Can you create sort of a plus what? Oh, can we create a plus one? You'd have to create a plus or minus one, and yes, but it loads more energy, and so you always get the plus or minus a half. Even in a passive system, I think a plus one will often split. So, yeah.
Why is plus 1/2
Just by symmetry, they've got to be forces and flows. Here's the flow field around it. Because you've got this shape, the order parameter changes, and so this grad Q term is non-zero, so they're going to be forces. Just by symmetry, they presumably have to be either that way or that way. And so you get a flow field set up which looks like this. Okay, so the thing moves. This one here, again, you get a flow field, but it looks like this. You get 6 vortices. Remember that, we'll probably see them in an experimental system if I get that far. Okay, and so this one doesn't move, but it does create a flow field. Is that okay? Yeah. Yes? Okay, so this is the experiment, and ask me again after that when if it doesn't make sense. So how does this translate into this microtubule motor system? And I'm going with this one because it's easier to see the defects. than it is for the swimmers, but the swimmers would be the same if you could sort of work out the direction of each of these little swimmers. This is a localized portion of the microtubule motor system. This is the top one is the thing buckling. So, oops, that's the, right, that's it. So this is it buckling, all right? And this is what happens as a function of time. And right at the beginning, people asked about these spaces. And you can see that this space here is this threefold symmetry of a -1/2 defect. And this one here is this shape of a +1/2 defect. They're being created here. And then the +1/2 is moving away from the -1/2. So that's the experimental version of what's going on. This is a bigger field of view. The dots are the +1/2 defects. Okay, we'll see the movies in a minute. The difference between the different frames, these guys are better fed, more molecular motors. Okay, and so what you get is more defects and smaller vortices. So this is definitely what you expect to happen here. Okay, so that's the experiment of actually seeing these things. Yes? It's tricky because Reynolds, this is a complex fluid, so it's not just a Reynolds number problem. We're a low Reynolds number here, but there are other dimensionless numbers. Essentially, the normal Reynolds number is 0, but you need to worry about the ratio of elasticity to activity as well. Yeah, there's a, oh gosh, what's it called? Yeah, sorry. I think you're asking about other dimensionless numbers. Yeah. And the important one is elasticity to activity. That tends to be important. And I can't remember exactly what value it takes here, but those are the two things, activity versus elasticity, which are the main control factors of what you see. Yes, if you scaled that number, you would end up with something similar, but you have to be a bit careful because it isn't the only dimensionless number. Activity, it's these little motors pushing these things. Yeah, little motors pushing the things. Yeah. Sorry. Sensitive to temperature. With biological things, you tend to stay at the same temperature because they die off if you don't. All right. I think if you increase the temperature, you can get them to move a bit faster, but then they'll be very unhappy soon. So temperature isn't a good thing if you're a biologist, right? You tend not to worry too much about it. All right, so we made it. That's the conclusions. That's where we've got to. This is the generic story of active pneumatics. This is how they work, and this is the physics behind them. These are two references which might be helpful if anybody wants to follow it up. The first is a review article we wrote, and the second one is a rather nice selection of very short review articles, which are meant to give you just where you start to look at any particular bit of a field. Now I'm going to just talk about one more thing, which I think is perhaps a bit more for the experts, and it's only 1.5 slides. Okay, so don't worry too much about this. And then I'll talk about, and then I'll see what I'm going to do next. I haven't decided really yet. Okay. And that is that we've assumed thermodynamic ordering, right? We've assumed that when this thing isn't active, it's a passive liquid crystal and it's in a nice ordered pneumatic state. And if you think about swimmers and you turn off the activity, you know, that it doesn't seem right, does it? It doesn't seem right that they will form a nice pneumatic state. Similarly with these microtubules and motor proteins, in fact, what they do is just clump up in a mess. So let's start with a system which has pneumatic molecules, but is actually in a what's called a paraneumatic state. So you're above the transition temperature, and these molecules are completely disordered. That would seem to be a more sensible starting point. So why can I still have active turbulence? And the answer is that there's a second instability, and Marana, wherever she is an expert on this, one of the people that sorted it out. And what this instability is that if you have an isotropic state, a completely random state where the nematogens are random like this, with an order parameter, I've called it S is equal to 0, the activity itself will drive that pneumatic. So it's something that's happening in the other direction from instability 1. Instability 1 took my pneumatic and destroyed it. This is another instability which takes an isotropic state and creates a pneumatic state. And so what would happen is these two instabilities will fight each other. So I'm going to explain in pictures how this instability works. Okay. Instabilities start from fluctuations. Let's put on a tiny fluctuation along this axis here, say, where this bit here is like a wave, if you like, where this bit's more ordered, that bit doesn't get ordered, that bit's more ordered. And so it's sort of like a wave fluctuation. And when I say more ordered, I've driven this, I've done this so it's ever so ordered, right? And that's overdoing it by a lot. It's just a little bit more ordered than that, but this is harder to see. So the blue things are the nematogens, and a fluctuation is driving them into this sort of pattern. And that, you know, there are going to be loads of fluctuations, and locally some of them are going to look like that. This is an extensile, therefore it sets flows. I've drawn the it sets up in red. Yep, it's extensile, so the flows come out from its ends and in from its sides. Same for this bit here. So if you look at the bit in the middle, you see it's subjected to a shear flow because you have a flow going upwards there and a flow coming downwards here. Yep. What happens with these things if you put them in a shear flow, actually, what they tend to do, because of the term that Leo was talking about at the beginning, is that they tend to line up with the shear flow. Those nematogens will tend to line up with the shear. And so this bit will start looking pneumatic, same as that bit and that bit. So that's how it works. You get this instability due to these shear flows, which tend to order it, even if it starts off not being ordered. But then this is pneumatic and the activity doesn't like that either. And so this is going to then decay back down again, and you get this continuous system. But even if you start with a completely isotropic state, you will get small pneumatic order and active turbulence. Yeah. That's right. It will change the scaling. It will look a bit different if the pneumatic order is thermodynamic or if it's caused by this. I don't understand what the right length scale is here. It's a good question. That's still research. Right. So how are we doing? Right. I might, should I do this bit? Yeah, I'll do this bit because it's fun. Yeah. All right. So we're going to end up almost certainly being in the wrong place at the end of the lecture, but I'll just carry on from where I'm going to from here because I do want to do confined active pneumatics. But first of all, I just wanted to show you this. This is up to now what we've done, I think, is pretty generic state of the art in the field. People are finding these topological defects all over the place in real systems. And this is just one example. And it's not a special example. It's just one we happen to have done. All right. And it's cute. But it's one of maybe about sort of 30 or 40 examples where topological defects seem to be doing things, although, you know, it's not going to solve the whole of biology, but there are places where they seem to be important. And this is the hare and the tortoise story. So what we were trying to do is see what happens if you have a mixture of two different sorts of bacteria. These are Pseudomonas. They're bacteria which don't swim, they crawl. They crawl by having these little pili things, which are little hairs, which they pull themselves around on the surface. And their motion is actually on average pneumatic because they go forwards and then backwards like this. Reasons which might be to stop them jamming, but we don't know. And the question was, what happens if you mix together two different sorts of these things, wild type, which I eventually worked out means they come sort of straight from the pond, all right, and genetically modified ones, which are genetically modified to have more of these pili, and so they go faster. So I've got a mixture of fast bacteria and slow bacteria. While we're at it, there is a question mark here, right? This looked like active turbulence. It was definitely turbulent-like, but it's different. You do not, these are not in a background fluid, right? So it's just like rods giving you active turbulence. I'll come back to that in a minute, but let's just say it for now. All right, so here we are. Here we have the cell speed and the PDF of how many cells. So the blue ones are the slow ones, and these ones here are the fast ones. You can see that there's definite difference in average speed, but there's a large distribution. So let's see how they grow. The colonies are growing from here, and they're growing in that direction. All right, we can see them grow. This at the top are the slow ones. These ones here are the fast ones, and these are where we tortured the things by taking all the pili off completely, so they're not meant to move much at all. All right, so those up there are slow. The ones in the middle are fast. At the moment, there's just one sort in each bit, and this is what happens. Okay, ones at the top are the slow ones, ones here are the fast ones. They are essentially spreading by moving. There's very little cell division there. Let me play it again, because this was very surprising. And this is why it's the hare and the tortoise story, right? The slow ones eventually win. And it would be nice to understand why. Just before you ask, these lines are just where you have to move the microscope stage, and they didn't cheat. Yep. So if you look at the front of the colony, so now I'm looking at the same thing, but rather than having two different sorts of bacteria, I've got a mixture of bacteria. All right, and just looking at the front of the colony, the blue ones are the slow ones. At early times, the front of the colony looks yellow, right, which are the fast ones, which you expect to win, expect to be much better. But at later times, the slow ones are winning. Something is happening to those fast bacteria, which means that they can't spread out as much as you would like. That's just with a few comments about persuading the referees that it's actually true. Yeah, okay. So what we did, I'm not sure why we did, but we looked at topological defects in these systems. I think we're just looking at topological defects everywhere, right? So these are the these are the topological defects you can identify in this system. It's looking locally like pneumatics, and so you ought to be able to find the topological defects. We also tried to model this. I mean, a sensible way of modeling would just be as rods. Okay, so they're just like rods. So if you're going to do them in a computer, you could do a continuum, but you could also do rods, yeah? And so this is the result of just having a load of rods, which actually are polar. They just move forwards and they have hard core interactions. So they can't overlap. So they just have a self-propulsion and no overlap. And as far as you can see, the defects look pretty much the same. Pictures of defects look pretty much the same. And let me just remind you, this is exactly what we had before. You could also do a continuum model and you get a load of defects like that. Now, let me preempt your question. why am I calling the topological defects the same in these three very different systems? You know, is it fair? Are they behaving in the same way? So we measured the flow field around these systems. So this is the flow field around the defects in the three different systems. This we've seen before, flow field around +0.5, flow field around -0.5. This is from a continuum model. This is this rod model, this rod simulation model. You can see same thing, same structure. Not so nice because you have fluctuations there. This is the flow field around a -0.5 defect. Okay. This is from the experiments. Again, you're seeing flow field around +0.5 defect. You can see the two loops. Here you can see the 6 vortices. Again, even more fluctuations here, so it's not so nice. But you're seeing essentially the same sort of flow field. You see essentially the same director structure because that's how we defined defects. So at least to a leading order approximation, you're seeing the same thing in these different systems. So why? I'm going to tell you the answer. All right, well, let's show you this. So if you look at one of these mixtures, look down on them, what you see is clumps appearing. Okay, and then this is the same thing starting again. You're getting these clumps. And what it turns out is these clumps are places where the fast bacteria are stuck. The fast bacteria tend to become stuck. And they're stuck in clumps where they're pointing away from the surface. So instead of going like this and twitching, they get themselves organized like that. And so what you're seeing here is these clumps of bacteria looking like that. And it turns out that what starts off these clumps are topological defects. What happens is that by chance, you have 2 +0.5 defects moving towards each other. And because of their flows, they tend to orbit around each other. Okay, they tend to move like that. And they tend to set up flows. And they tend to set up flows which push these guys here to point out of the plane. Right, it's not obvious, but if you look at it, that's what's happening. I'll show you some evidence, all right? So just by chance, +0.5s come together, they move like this, and they push bacteria, so they're stuck on their ends, and then other bacteria come in and join them and form these clumps.
Come in slightly different heights.
We're in 2D, right, to start with, slightly different, yeah.
They're at slightly different heights.
Slightly different angles, yeah, and then the flow field pushes them up, yeah. That's right, that's exactly the right question and exactly what I should have said. I'm going to say next, right? This pushing up is much more efficient if the defects are moving fast, and the defects are moving fast if the bacteria are fast. What happens is that the slow moving ones sort of manage to do this and flop back down again, and the fast moving ones do that and get stuck. Yeah?
So it's not that you have more defects, it's just that defects are spinning around each other more frequently.
I think when they spin, they're moving faster. This is a sort of computer simulation to show that. The one on the left is 2 defects coming in slowly. Oh, that's it. Let's go back to where we're meant to be. Right, the one on the left is 2 defects coming in slowly. Things point towards you, but then flop back down again. The one on the right is 2 defects coming in fast. And you get a colony which stays upwards. Okay. Another picture. Slow, medium, fast. Computer simulation of what's going on. You can see slow, you can see medium, you can see fast, and the fast ones are much more efficient in making these pointing upwards colonies. Yeah. In the simulations or in reality? In reality. Okay, so what they're doing is that they start moving around on this desk, right? There's just one layer of them and they're moving like this. And there'll be a couple of defects doing that. The defects produce flows which can push upwards because they're sort of got water above them to a first approximation and they go whoop. Yeah. Okay. Yeah. Essentially, when things are moved up out of the plane, that's the same as the defects disappearing. They just get stuck. Okay. In the simulations, we have to cheat a bit, and you know, well, actually, the way we have to treat is to make it so it's not too easy for them to move up, or they would move up very, very easily. I'll show you a real experiment in a minute, just to prove that it actually happens. Yeah. It's reasonable that it would be, but I think you have to look and see if that happens. Yeah, okay, because their little feelers are sort of wiggling around in space by then. It happens and it makes sense, but it's not obvious. It has to happen. Yeah, yeah. Yep. It doesn't scale like that. The slow ones never have enough energy to do it, and the fast ones do. Yeah.
Could you observe the same results if bacteria were forced to stay in plane, but some sort of motility-induced phase separation type phenomenon?
No, this is different from MIPS. It really is not MIPS. No. Yeah. In the simulations, we just have hardcore interactions. What we find we have to do is, I mean, there is a cheat in the simulations, which is that we have a potential which holds them down because they actually want to zoom up much too easily. And that's fine, because in the experiments, you actually put a layer of, what's that stuff that they eat from glassy stuff on top of them, agar. Yeah, yeah. You get the defects, but they wouldn't pop up. You still get the defects because the defects are a 2D thing. They're a two-dimensional thing. Well, you couldn't, because if you constrain them to the plane, right, they couldn't pop up. So you're killing it before you start. Yeah. Yes, lady behind you. As far as we could see, yes, that you need that sort of flow field. Yes. It looks like you need the flows, but that's a very good point. That certainly was my first guess. Right, can I just show you the real experiments, and then I'm very happy to answer questions, just because, you know, I mean, in a way, we mock the simulations. You're choosing parameters so it works, so it's only fair to have experiments. I did this second because it's quite hard to see what's going on. All right, what you will see here is a movie. We see the defects, and then this thing here is going to be a popped up region. I mean, these are Ollie Meacock's experiments. They are, I mean, just finding these things, they're tiny, right? Finding the right bit is amazing. This is a picture of the end. Here you can see the popped up region, and you see it's mostly yellow. The fast ones get stuck here, okay? What we haven't sorted out, we didn't sort out at the time, I think we still need to sort out, is that once the core is formed, why do you get more fast ones arriving? But that sort of makes sense, right? That you'd expect the fast ones to hit more often and therefore to get stuck more often. Here's a sideways view where you can see this verticalized colony forming, where this is meant to be vertical. Yep, and you can see that it tends to be the yellow fast ones. So let me show you the movie, which is probably the least, one of the most beautiful movies, but actually looks not very beautiful. Okay, so those are these guys forming in the middle. And these are the color-coded versions of that. Let me play it again. Yeah. All right, and then that is just a summary. All right, so now questions. If anybody would like to ask questions, yes? Jamming will have a bit to do with it, but not really, because you actually want a system that's moving, because that's the defects wouldn't move themselves. I guess, well, eventually the whole lot would just flip up. That's right. We didn't do that, but you would expect that the whole lot would just stand up eventually. Go on. Sorry, you mean how wide they are? Yes, they keep time. Yeah, yeah.
I wanted to come back to this connection to the number of legs.
Mm-hmm.
So one way of interpreting this be somehow back to the biology that there's been a selection for the wild type legs, whatever number.
Yeah, I mean, that's certainly what the biologist immediately said. That's right, that these things, it would be really good if they could move fast, so they grow more legs and move fast, and that would be better in theory, so they can increase their range, but then they get stopped. And so they have the right number of legs, which is just on the edge of this happening, if that's right, yes. Yeah?
With the characteristic bunch size from the size of bacteria and their velocity, or do you need more dimensional constants?
You mean the size of these bits that are standing up? It grows with time, because once the defects initiate them, but then more bacteria arrive and stick up. There's no steady state size, no. Although we haven't followed the movies I showed is as far as we've got. Yeah, yeah, yeah. No idea. These are really hard experiments, and they're parameters like that we haven't varied, and it would be interesting to do in simulations, at least to start with. There are all sorts of questions about active turbulence in these rod systems. I've argued it's more or less the same as the ordinary active pneumatics, and that's a first approximation, and I don't believe it's true, but we're really at the edge of research there. So it's perhaps not a good time. Yeah. You mean in the popped up bits?
No.
Or, no. I mean, again, that's getting towards why these things are probably a little bit different from the fluids. We did structures, yes. Do you mind if I'm very happy to talk to you afterwards, but I don't have a coherent story because it's research and we don't quite know, but yeah. Hello, yeah. No, you're okay because you've got the third dimension coming in. This topological charge only works if you stick in 2D. That lady in that one, yeah.
So I don't think it's perfectly. The life type is more efficient at dividing. So first we can show the stripes. It's very difficult to compare the three of them because they may be kind of the alignment like you mentioned, but also they divide and they split the volume.
Our experimental colleagues looked at the division, and it's a small contribution in each case. Yeah, but you're right, you do have to worry about that. Yeah, so question back there. Sorry, I didn't hear that. Yeah. Yeah. Yes, but if I looked a bit further away, it would look different because the extra thing in the dry and active pneumatics is friction, and that screens the flow. And again, no one's quite sure about exactly the differences between those two things. Yeah. Oh. Mm. I mean, here, once things have popped up, you have to stop thinking of it in terms of these sorts of defects, because the defect story, story, and the topological constraints can escape in the third dimension. That's what makes these difference. Yeah. In passive systems, you get defects, but they're not motile defects, and they can be destroyed but not created. In 3D, we'll come to that later. All right, yeah. I mean, I love answering questions, but as long as everybody else is happy. Yeah. Yeah. What instability? So I didn't understand the word. What did you call the instability? Can someone help me? Oh, linear instability. Sorry. Yes. Yes. Yes, that's linear instability. Yes, but the molecules themselves, the nematogens, have this symmetry. It wouldn't work if I had an isotropic fluid. All right, so it has to be described by Q tensor. Yeah. Yeah. Yes. 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 Yeah, these things live on surfaces. They sort of cause biofilms. So this is an early stage in a biofilm. They will form more layers, but to start with, they look like, indeed, this might be what nucleates the biofilm formation, but we don't know. Yeah.
Plus and minus one pattern also come to like
Yes, yes. Plus and minuses are always appear in pairs. No, because only the plus one have the dynamics to form this vertical system. Yeah. Am I thinking? Yes. All right. Yeah. No, we didn't. It would be really hard to look at the interface growth. I think just the rate of growth is something which we might look at and would like to do, but you know, I think there are rod simulations which we can do. I hope we'll carry on with this. Hard to get people to do the experiments. They're hard experiments. Yeah.
Evolutionarily an advantage to expand faster?
Well, you think so, yeah, because you want to beat other sorts of bacteria. So most things that is true. But if you do it too quickly, we're saying that they get stuck. So the wild type have probably got it right, which, you know, who knows if that's the story or not. Okay, yes.
So once that volume is formed, if you switch up the or decrease the velocity, will it disappear or?
No, they get stuck. I mean, what the actual bacteria, they're doing my simulations, but the actual bacteria will sort of form starchy-like connections between themselves as they do in a biofilm. So they do demonstrably stay there. Yeah. That was something which the referees, oh, sorry, yes. Yeah, the problem was that, you know, maybe it's a different mechanism, because if these things have got more pili, they're more sticky to each other. And that was something that the referees were worried about. You know, my experimental colleagues, we tried very hard to try different things, and it looked like no. I'd have to look back at the paper to know, but I mean, that was something one should worry about. They're very small, but certainly you could imagine that the interactions change because of the pili, and that's what you'd have to worry about. But we can actually see these defects, which makes it a bit more real. I'm going to, given we have to finish dead on time, I want to just say one more thing and then show you a movie, and then I'm happy to take questions until past. But I need, is that all right? It's just, yeah, this one. Because this story, this hare and the tortoise story is special, right? All bacteria do not behave like this. It's just a rather cute example, although there are quite a lot of cute examples, some of which I'll show you tomorrow. But let me just show you another one today, because it's another bacteria story where, again, topological defects are important, but the underlying way it works is very different. This is work which is actually published back-to-back with ours in Nature Physics. What you're seeing here is this chap, this mixed coccus, and the different browns are different layers. So now what this thing does is it stays in plane, so it's middling like that, but then it forms a second layer on top that still moves in plane, second layer on top, and so on. And what they found is that the place where the second layer starts forming is a +1/2 topological defect. And then the third layer again is a +1/2 topological defect in the second layer. Sometimes you get gaps in the layers, and the places the gaps in the layers form are at -1/2 topological defect. So it's another example where the formation of biofilms is relevant to the existence of these topological defects. And again, the reason is that the flow fields around the defects, different now, are tending to push things into a layer or tending to push them apart. It's a bit difficult to see on the movie, right? You'd have to look at the correlations better, but this is just the different layers forming and unforming. The correlations between the defects and the spaces is a bit tricky, but you could see that this one grows from that -1/2 topological defect, for example. So again, it's a small example, but it's another example of where these things form. So the last slide I want to show you is this one, because oops, sorry. It might have sound by mistake, sorry about this. You want to do sound? Oh, maybe not. Oh, good, it hasn't got the sound because it's a bit noisy. All right, this is just so you'll remember something. Okay, great. All right, so I'm going to stop there, and tomorrow I want to talk about confined systems and show you that the transition to turbulence in these confined systems is actually the same as you get in inertial turbulence for reasons I don't understand. And I'll talk a little bit about 3 dimensions, and then how we get this same sort of active turbulence in squishy cells. Now, what do you want to do time-wise? I'm happy to take questions.
We have 5 questions.
Has anybody got other questions? I think they probably had enough. Let's stop there, and yeah, and I'll be walking towards the field, very happy to answer questions.